So my name is Vivek, and I'm a machine learning engineer here at Vectara, and I'll be talking about dissecting the R in RAG. So as Forrest already talked about, R stands for retrieval, and basically there are two sections that I'm gonna split this into. So the first is the impact of retrieval on RAG systems. So like how the performance of retrieval would actually impact the final output of your RAG system, and then we'll break down the state-of-the-art retrieval and basically do a small dive into how do you build a state-of-the-art retrieval engine. So moving on, and so why exactly is retrieval important? So as I tried like to put it, retrieval is the source of truth for the RAG system, and without effective retrieval, it's really, really difficult to get a very good answer out of a RAG system, and this is better illustrated in a couple of examples that I have over here. So basically, I create this RAG pipeline. What I did was I took a bunch of documents or pages from Wikipedia and I indexed them. And I then run a query over these documents and try to summarize the retrieved results using a large language model. And the only difference between the system on the left and the system on the right is the retrieval engine. So I'm using two different retrieval engines. So here in this case, when we ask the question, when did Great Britain colonize Australia? You see that the first system did not, the LLM isn't able to narrow down to the answer because the retrieval was poor. Whereas in the second one, because we were able to get the facts, it kind of frames the answer for you. So this is like one of the cases where the retrieval was totally off and wasn't able to pinpoint the exact snippet where the answer was in the documents. There's another more subtle case where it kind of would affect your user experience. So in this question, like where does Rhine end? Rhine being a river in Europe. So here, both these systems kind of generate summaries. So when you read through it, so the Rhine River begins in the Swiss Alps and flows through several countries, forming borders along the way. It passes through the Rhineland region and eventually empties into the North Sea in the Netherlands. So basically, if you read through this whole text, you can try to infer, okay, that this snippet does answer your question to some extent, that the river ends in the North Sea in the Netherlands, but it's not very highlighted by the answer. Whereas in the second point, where the retrieval is bang on, so it directly states that the Rhine River ends in the Rhine-Meuse Delta in the Netherlands near the Dutch-German border. So this basically gives you a more accurate answer. So here, this basically emphasizes how small nuances in retrieval can significantly change the quality of the answer that you get out of the RAG system. So let's move forward. And now let's talk about the different parts or the different components of a retrieval pipeline. So starting off, so basically what is the goal of a retrieval pipeline? So a retrieval pipeline has two goals. You have heaps and heaps of data. So it first needs to fetch in all the relevant information that you have inside your data. And then it needs to rank those results or the relevant information that it found into an order where the document or the result that's the topmost should be the most relevant to the query that we issue. So there are multiple ways to do this. A couple of the most common ways are keyword-based search and neural search. So I'll go through them briefly. So what keyword-based search does is that it tries to find overlapping keywords or overlapping words between the query and the document. And so if it finds a significant number of overlaps, like exact word matches between a query and a document, it would classify the document to be relevant to that query. Whereas in neural search uses end-to-end deep learning techniques where it tries to find the semantic meaning of your query in the document and then tries to match those semantic meanings. So for example, let's say a user issues a query, let's say dog food, to some data. So neural search will also try to match documents that are titled, let's say, puppy food, because this system would understand that dog and puppy are closely related to each other. Whereas a keyword-based search is very likely to fail in this scenario because it cannot find an overlapping word like dog and puppy together. Another example where like neural search might perform inferior to a keyword-based search is like if you issue, especially with named entities and stuff like if it was not trained on something or a very new word. So for example, let's say we have a neural search system that was trained on data before 2020, before the word COVID became so much more popular. So this kind of a system might have issues, like if not being retrained using the latest data, might have issues with like finding what matching documents with the word COVID. But the keyword-based system would form perfectly fine over here. So usually what we do is we try to get the best of both worlds. So we use hybrid search. So hybrid search runs both a query against both these systems in parallel. So it would fetch the results from keyword-based search, it would fetch results from neural search, and then try to create a single ranked list by combining those two search results. So in this talk, however, we'll be mainly talking about neural search and dive more into it. So starting off with neural search. So to enable neural search, we use a class of deep learning models called as text embedding models. And what these models do is that they take a piece of text and they generate an n-dimensional vector. But an n-dimensional vector means that it's a list of n floating point numbers. So once you have those numbers, so what exactly do these numbers mean? So basically, what we do, if we map these vectors into an n-dimensional space, vectors that correspond to text that have similar meaning to each other would lie much more closer to each other in that embedding space. So for example, here, if you see the image over here, so we have these vector representations. So this is just a dummy. And puppy and dog, because they are very closely related, lie very close to each other in this space, whereas cat is kind of nearby, but not as close. But however, another example, houses, lies much more away from puppy and dog. This is just because words that, again, stressing upon the fact that words that mean the same thing lie close to each other. So going forward, so how exactly do we get to this embedding space and how exactly do we learn this embedding space? So to do that, we train a class of models which are commonly known as dual encoder models. So by dual encoder models, what I mean is that we have two different models. There's one model that would generate the query encoding or the vector representation for the query, and another model that would generate the vector representation for the document. And when we try to learn these models, what we do is, once we have a vector representation for the query and a vector representation for the document, we try to maximize the similarity between a query and a relevant document. And at the same time, we also try to minimize the similarity between the query and a non-relevant document. So when we do multiple iterations with loads and loads of data, that's the type of embedding space that these models learn, and which then enables us to perform neural search on top of it. So this is just one of the variations of the model. There can be multiple variations where the query and the document encoders could share the parameters. So you have one single model that does both, that also generates the query embeddings and that also generates the document embeddings. However, there's a catch over here. And the catch being that whenever we use these models, the query and the document embeddings must be generated separately. At a given point of time, the document, the model should not see or should not process the query and the document together. And the reason for doing that, I'll cover in just a bit. So basically, the only interaction, any kind of an interaction between the query and the document only happens to compute the similarity between them, and there's no interaction before that. And the reason why we need to do this is because how we use these models while we run inference. So to use these models during inference, what we do, we pre-compute the document embeddings using the document encoder, and these embeddings are then stored in a vector database. And so this constraint that is enabled because so basically this thing that pre-computing of the document embeddings can only be done because when we are learning the document embeddings, it is done independent of the query, and there's no interaction between the query and the document. So this whole thing makes the system much more scalable, and this is why it enables dual encoders to run for millions and millions of documents. And so then when we get a query, we would in an online fashion, we would generate or try to encode the query and then run a nearest neighbor search on the vector database, and then finally the documents can be ranked based on the similarity score for the vectors that we get. So this is all good, but we do have to ask the question can we improve this system even further? And the answer to that is yes. And how exactly, now let's talk about how exactly we can do that. So the one thing usually for all these models, we use transformer-based architectures. And one thing that was enabled by the transformer-based architectures was the interaction between each and for a given piece of text in a transformer architecture, each and every token interacts with each and every other token. So in the image over here, if you look at this example, so there are different varies of transaction, or basically how I would read this image is that the more bolder the line is, the more heavily that word focuses on itself. So that's basically the self-attention operation that happens through different layers of the transformers. So basically, if you look at this first snippet over here, the state will never be perfect. And so basically, state pays a lot of focus on words like the, never, be perfect. So let's say when we ask a question, what will never be perfect? So this kind of interaction helps the model figure out that the answer should be state, because these words kind of have very heavy interaction or heavy attention paid on the word state. So this basically takes us to a new kind of model, or the exact architecture that I was talking about, known as cross-encoders. So what we do in these kind of models is, previously we talked about like generating the query embedding separately, having the document embedding separately. So here we concatenate the query and document into a single piece of text and pass this text to the model and ask the model to produce a relevant score out of it. So basically, whatever score the model generates can be interpreted in the way how relevant is this document to this query. So as you can see, so this is the standard transformer architecture. Basically, all tokens interact with everything, and finally we get a relevant score out of it. So now basically, how do we train these kinds of models? So these kind of models can be trained in a fairly simple fashion. Like you can consider them to be a text classification problem. So for a text classification problem, what we do, we have a query. So basically, if we treat it as a classification problem, we can look at it as a query document. The input data will be in the form of a query document and a label. The label would be 1 if the document is relevant to the query, or it could be 0 if the document is not relevant to the query. And we just treat it as a standard classification problem and train the model. Whereas another way could be to train it as a binary ranking problem, which is much more closer to what we are trying to achieve with this problem. So basically, then we have the input data is in the form of query. So the input data is on the form of query, relevant document, and non-relevant document. And the aim of the model with this type of data is to provide a higher score to the relevant document as compared to the non-relevant document. So these are just like a couple of very basic ways on how you could get started with training these kind of models. And so finally, like how do we use them during inference? So during inference, this model takes query document pairs. So let's say you want to generate a ranking of 10 documents for a given query. So one query and 10 documents would generate 10 query document pairs. And then we would pass all of these pairs individually to the model and get a list of scores, and then sort the documents based on the relevant score that we get out of this model. Because of this, because every query needs to interact with every document, you can see that the runtime scales linearly with the number of documents that we have for a given query. And so therefore, the usage of these models is much more limited, as it would not scale. So let's say if you have millions and millions of documents, you would have to do millions and millions of passes through the model for one single query, which does not scale very well. And therefore, this kind of models are usually used on the output of the dual encoder model, where you get, let's say, 50 or 100 results from the dual encoder, and then you ask such a special model to re-rank those results to generate an even better ranking. So in order to now summarize everything we just covered, so basically we talked about two kind of architectures, that a dual encoder architecture and a cross encoder architecture. Dual encoder architecture encodes the query and the document separately, and we then computes a relevant score out of it, whereas the cross encoder architecture would simply encode both of them together, allowing full interaction between a query and a document, and then emit the relevant score. So basically, what are the use cases and when do we want to use which of these models? So a dual encoder is a more general purpose model and can be used for searching over large and large amounts of data and for general purpose search, whereas cross encoders can be used as an additional performance boosting step on top of the output of a dual encoder model. And we can also have different types of cross encoders that we have for niche use cases for doing domain specific rankings. So, but all in all, to sum it up, like it should usually be used on small amount of data because of scalability issues. And so like one sample use case that we can go through to ensure like how different these models work. So let's say we are trying to find similar documents and we have a collection of 10,000 documents. So in order to do that with a dual encoder, you would need 10,000 passes to compute the embeddings of these 10,000 documents. And then once you have this matrix of 10,000 embeddings, you just take a dot product with itself and you compute the similarity scores. But doing the same with cross encoders would require 50 million passes because you would have to do pairwise scoring of each of those 50 million pairs that you get out of the 10,000 documents. So finally, what's the suggested way to use is like have a strong dual encoder doing the initial retrieval and then re-rank those encoders based re-rank the results of the dual encoder based on the cross encoder. And this is something like Vectara offers out of the box without any tuning of the retrieval and the re-ranker. You get state-of-the-art retrieval just by uploading your documents and signing up. So yeah, that's all from us.